Good morning, ladies and gentlemen. My name is Wang, the PhD candidate of Texas Tech University, and today I'd like to give a presentation on our recent research, the PAC, the Paged Adaptive Coalescer for 3D stacked memory. I'll first talk about the introduction, the background, and the related motivation of our research. Then I'll go through the details of the PAC design, the evaluations, and the conclusion. So driven by the ever-growing trend of the size of the datasets, data-intensive computing gradually becomes a popular topic. Some well-known data-intensive algorithms and applications include the sparse data structures, the big data, the graph analysis, network theory, machine learning, and so on. And one of the characteristic of the data-intensive applications is actually the irregular requested distributions, or let's say the irregular memory access patterns. For instance, the scatter operation, as we can see here, is actually using the array A with the index bi equal to ci. Notably, the index of the bi here, the value is actually random. So as a result, if we plot the corresponding requested distributions in the main memory, we will be able to see something like this. And all the crosses here represent a physical memory request. And we actually record 10,000 cycles of the time frame. And on the y-axis, as we can see here, is actually the physical address of the corresponding memory request. And the x-axis is actually the corresponding time. So the random memory access patterns are non-deterministic, and it will cause a frequent cache misses and a massive memory requests. And this is actually one of the biggest challenge of the data-intensive application. So driven by the challenge of the irregular workloads, the 3D stacked memory is introduced. As we can see here, this is actually an example layout of the 3D stacked memory. On top of the 3D stacked memory is actually the multiple DRAM dies stacked over the logical die, which is actually the memory controller of the 3D stacked memory. The 3D stacked memory relies on the thousands of high-speed TSVs to transfer the data across different DRAM dies, so they can provide a sufficient amount of internal bandwidth, and also they use the high-speed links between the processor die and the 3D stacked memory die to provide a sufficient amount of the bandwidth. And some well-known products, as we can find on the market, the first one is the HMC from the Micron, or the HBM from Intel. And a single HMC device can provide up to like 320 gigabytes per second, which is 15 times the performance improvement as compared to the traditional DDR3. And in 3D stacked memory, they actually require, or let's say desire, the large request to fully exploit its throughput. And however, the cache-based mishandling policy potentially limits the request granularity to the 64-byte request in the mainstream architectures. Therefore, dynamic memory coalescing, also known as DMC, is desired to boost the performance of the 3D stacked memory. The memory coalescing can actually save the power of the 3D stacked memory. As we can see on the figure here, we actually plotted the power distribution of different operations within the 3D stacked memory. As we can see here, the majority of the power cost results from the buffering the request in each let's say the vault, which is actually the controller of the 3D stacked memory, or the link usage between the processor die and the 3D stacked memory die. So if we reduce the number of requests flushed into the main memory, then the memory coalescing can potentially reduces the redundant the data transfer over the serial links of the 3D stacked memory. And also, if we eliminate the redundant request flushed into the actual DRAM, then we can also save the power cost of the vault controller or the channel controller of the 3D stacked memory, which is actually used to buffer the request in the request slot or the response slot. And also, DMC can help enhance the performance of the 3D stacked memory. So first, by reducing the number of the memory accesses to the 3D stacked memory, we can actually combine the DRAM row accesses to minimize the corresponding latency. And it actually fits the closed page policy, which is actually optimized for the regular workloads in the 3D stack memory, such as the HMC. And we actually tested within the 3D stack memory if we employ the open page policy. And as we can see on the figure here, over various data-intensive workloads that exhibit the irregular memory access patterns, the majority of the DRAM accesses will actually cause the row buffer miss. As a result, that's actually the reason why that for the regular workloads and data-intensive workloads, the closed page policy is usually employed to improve the performance. And that's the reason why the DMC could further benefit the performance for the 3D stack memory and irregular memory access patterns. So for the existing work of the memory coalescing in GPU, they actually relies on the GPU Coalescer to aggregate the intra-warp requests hitting the same line of the L1 cache. And similarly, in the normal processors, they have the miss status holding register, also known as MSHR, to merge the misses of the same cache line of the lost level data cache. And the similar case for the architecture that actually employ the 3D stacked memory, such as the Fujitsu A64FX, they actually introduced a combined gather operation to combine the accesses, load accesses to the L1 data cache. However, there's no such an optimization that is dedicated for the 3D stack memory has been employed in such architectures. Therefore, given the limitation of the conventional DMC methodologies, such as the Coalescer request size is fixed to the width of the cache line, typically 64 bytes, and also limited bandwidth utilizations because of the transferring the small request, and also limited performance of the request aggregations, given the granularity of the combined or let's say aggregated request. Because traditionally, let's say MSHR based or the cache based memory coalescing models, they usually limit the request size to the 64 byte. They cannot, let's say, combine or aggregate the request that actually mapped to adjacent cache lines. Therefore, a new DMC model optimized for 3D stacked memory is desired. And in order to better design the memory coalescing model for the 3D stacked memory, we first investigated the distribution of the aggregated requests of various applications. And then we actually tested the proportion of the requests that aggregated across the OS page boundary. As we can see on the figure here, over the tested benchmark, majority of the requests are actually the requests that can be aggregated actually reside within the same OS page, and no more than 0.2% of the requests could be coalesced across the physical page boundary. And as a result, we don't really need to waste the time to compare and coalesce requests that are distributed over different physical pages or the virtual pages to further improve the efficiency of the memory coalescing design. And therefore, we introduced the page adaptive coalescer to aggregate the request for the 3D stacked memory. And that actually uses the OS page as the granularity of the memory coalescing to avoid redundant comparisons with requests following distinct pages. And it actually has some advantage for the multiprocessing or even virtualizations that can be very helpful, especially for the applications running on the cloud server, that one single node could be shared to multiple users, and have the multiple applications running simultaneously can further complicate the memory access patterns and corresponding latency. So first, the architecture of the PAC design. As we can see on the figure here, within the processor package, we actually introduced one component called PAC, as we can see over here, between the MSHR and the miss queue and write back queue. So pretty much we are actually aggregating the request after the last level data cache. So all the misses to the LLC will be coalesced by the PAC, and then flush the request to the MSHR, and eventually route all the requests to the 3D stacked memory. And the PAC consists of three main components. including the page request aggregator, the block map decoder, and request assembler. And we also have a network controller that connected to the first component, the page request aggregator, which actually manages the request ordering and some related optimizations. And each component will be introduced in the following slides in detail. And because of the request is actually the requests are actually being aggregated, and the aggregated request size will be larger than the single cache line. So the traditional the cache line sized MSHR entries cannot be directly used to hold the request that is larger than 64 bytes. Therefore, we made some extensions. So as we can see here, in the MSHR entry, we introduced OP bits, which actually represents the corresponding request types. We just want to ensure that we are not combining the requests with different request types. So because the load and store requests cannot be coalesced together, so we try to separate them. And also for the MSHR sub-entries, we introduced an index bits, which represents the corresponding the cache lines that has been referenced for each like a memory request from each the cores or thread. The index bits, the size of the index bits actually depend on the corresponding the DRAM row buffer size. So if the row buffer size is large, then we're gonna partition it into multiple chunks of the cache blocks and use that as an index for the corresponding block index to put into the MSHR sub-entries. So every time we just need to check a bitmap data structure within the MSHR sub-entries to determine which cache line is actually requested by this single request. And first, I will talk about the page request aggregator. It actually consists of the multiple coalescing streams. So in each coalescing stream, we first have a C bit, which represents the coalescing bit. And it will be set to 1 if more than one request fall into the same coalescing stream, representing that there is a possibility that we can coalesce the requests. Otherwise, the coalescing bit will remain 0, and it's going to skip the following the pipelines and directly flush the request into the main memory. Second one is the T bit, representing the request type, a 0 for read and 1 for write. And it will be compared as a part of the physical page number. So as a result, we can use the hardware comparators to directly compare the physical page together with the request type to ensure that the request, the same type of the request falling into the same physical page, will be put into the one coalescing stream. And we're gonna also update the block map, which is also a bitmap data structure representing which cache block has been referenced within this OS page. So the block map is actually a bitmap of the cache blocks within the same physical page. If a cache block is accessed, then the corresponding bit is set to 1. So here's actually one of the examples. As we can see on the top of the figure is actually the common address of the memory requests. So besides the virtual pages and the type bit is actually the page offset. And now we just partition the page offset into two segments. One is the cache block number, and then the rest one is the rest of the page offset will be the offset within the cache block, which remains unchanged usually. So in this example, the request block number is actually equal to 2. Then we are just going to set the corresponding bit in the block map to 1, representing that this cache block has been referenced or requested by one of the requests that is currently buffered in the coalescing stream. And then after we have the block map ready, we can just flush it to the second stage, which is actually the block map decoder, which is responsible for decoding the block map to attain the access bit sequences. And all the sequences will be flushed into the corresponding index buffer. The width of the sequence depends on the upper limit of the request size. For instance, in the HMC, the maximum request size is limited to 256 bytes. As a result, we only need the corresponding bit sequence of the produced by the block map decoder will be limited to 4 bits, representing 4 cache blocks at most of the aggregated request size. And the third one is actually the stage 3 of the pipeline. It's actually the request assembler. It is responsible to generate the aggregated request based on the protocols of the 3D-Stacked memory devices. As we can see here, the request assembler actually connecting to a coalescing table, which is actually used to determine the aggregated request size. And then the aggregated request will be flushed out to the corresponding MSHRs. So as mentioned earlier, the coalescing table is just a lookup table to check the corresponding request size. The block sequences are used as index to reference the respective request size. And this is actually one of the examples, shows how the coalescing table works. On the left of the coalescing table, left column is actually the block layout, which is actually the block sequence, also that's used as an index to reference to actually check the coalescing table. So, for instance, like on the second row of the coalescing table is actually the 0001, representing only one cache block has been referenced, no matter how many requests it has already been coalesced. So, as a result, the aggregated request size will remain 1. And also, as we can see, the block layout that has been marked in red is with the sequence 0110, which means actually there are 2 cache blocks are referenced within the this aggregated request. So as a result, we only need a 128-bit memory request. So as a result, the request size will be equal to 2, representing 2 cache blocks. And here is actually one of the examples of our memory coalescing models. So on the first stage, we have 5 requests ready for coalescing. It'll be flushed to the corresponding coalescing streams based on their physical page number and request types. As we can see here, because we also have the T-bit set as well, will be compared as a part of the physical page number. So for the request 4 and 5, even though they're accessing the same physical page, however, they have the different request type, which will be, as a result, flushed into 2 separate coalescing streams. As we can see here, notably for the coalescing stream number 3, they only have like one request, which is actually the request 3. Therefore, there's no such a possibility that in this coalescing stream will contain a request that could be coalesced because there's only one request. So the C-bit will be set to 0, remains 0, and it will bypass the following coalescing stages and directly flush to the main memory, which is just a normal cache line sized request. So for the stage 2, the request will be flushed to the decoder and generates the corresponding block sequences, which is 0110 because the 2 consecutive cache blocks are referenced. As a result, the corresponding coalescing table entries will be fetched, and it turns out that okay, this it represents like a 2 cache block request. So eventually, they're gonna generate a 2 separate 128 bytes memory request, which actually try to serve the request of the request 1 and request 4, and the second one for the request 2 plus request 5. And we actually implemented the PAC in the extended RISC-V spike simulator and used HMCSIM for the performance measurement. We also evaluated the various test suites such as HBCG, SSCA, bots, the NASA parallel benchmark, and the gaps, and so on. And as shown on the table here is actually the detailed environment configurations. So first, we actually test the coalescing efficiency, which is actually the percentage of the reduced request derived from the number of reduced requests divided by the total number of requests. And as we can see here, the PAC has achieved an impressive amount of the request reductions as compared to the conventional MSHR-based dynamic memory coalescing model, which is actually fixed the request aggregated request size to the 64 bytes. And on average, we reach almost like 56% of the request reduction of the PAC. And then notably, some of the benchmarks even show the coalescing efficiency over 70%, such as the EP, the scatter gather, the LU, MG, and so on. Then we also tested the case of multiprocessing. So instead of running a single application within the same processor, now we're booting 2 different applications with completely different memory access patterns, running within the same processor but on different cores. As we can see here, we witnessed almost like 50% performance degradation on the average coalescing efficiency when using the MSHR-based DMC. And oppositely, only 12% performance degradation is witnessed, or let's say the request reduction is witnessed when using the PAC. This actually representing like a more stable performance in terms of the request reduction of the PAC design in the case of the multiprocessing. Then we also tested the case of the power saving. The power saving overall is actually proportional to the request reductions in the 3D-stacked memory, benefited from the power saving on the request queue and the response queue, and also the high-speed link usage. And the PAC further reduces like almost like 33% of the redundant energy consumption compared to the MSTR-based DMC model. And eventually, we tested the overall performance gain of the PAC design. And compared with the traditional MSTR-based DMC model, the PAC outperformed it by an average of almost 38% over all the tested workloads. And the performance gain of the scatter and gather, and also the sparse RU, the SP, the stream even reaches over 20%, demonstrating the performance impacts of the proposed PAC design. So in this work, we present the PAC, a novel page adaptive coalescer for 3D-stacked memory, and in regular data-intensive workloads. We introduce a memory coalescing methodology built upon a pipeline coalesced network and adaptive MSHRs. The evaluation results validate the superiority or the advantage of the PAC from the perspective of request reduction, the power saving, performance gain, and so on. Due to the limitation of the presentation time, we didn't include all the results into this presentation, but you can find the details in our paper if you're interested. And we are grateful for all the reviewers of the HPDC committee and also our cheffer, Dr. Andrew Chen, for their valuable feedbacks and suggestions that help further improve this research. And I also thank you for watching this presentation, and please visit our website for details of the related research. And we'll be more than happy to answer all the questions related to this paper in the Q&A session of the HPDC conference. Thank you.